Okay, so welcome to GEO 420, and it's April 8th, 2021, and we're gonna start developing some theory for interpreting some of our data that we've collected and developing conceptual and numerical or analytical models for the MDOT site. So we're going to start off. The first well that we measured was M.1, and that was in the fractured bedrock, right? And so what we're going to do today is just talk about, or the first thing we're going to do is talk about how fracture systems are different and how fractured groundwater flow is different. So let's start off with some vocabulary and some nomenclature. So I'm going to draw, I'm going to attempt to draw here two sets of parallel fractures. So we've got a block here. I don't know why this is so hard for me today. Okay, so here's a block. Here's another block. Here's another block. And these blocks are intact rock. And in the fracture world, we call these intact blocks of rock. And these, obviously have some third dimension here that I'm not going to fully flesh out, but they sort of go in and out of the screen here. So in the fracture world, these blocks of intact rock gets called matrix. And this is intact rock. All right, and the matrix is whatever kind of rock you're in. So up in, for MDOT, we were up in the belt rock. So this is some kind of, mudstone thing. As an example. So e.g. So MDOT, we were in a mudstone / dolomite. All right, so when I say matrix, whenever I say matrix, I'm referring to the intact rock, whatever it is. All right, these matrix blocks are separated here by a fracture. So this is a fracture. Now, the fractures Here I've drawn, there's purely open space between these matrix blocks, all right? The fractures can be full of other stuff, sand or whatever. For now, let's consider open fractures. So this is open crack between matrix blocks. And as another note, it really it can be filled with sand or other material. But for now, we're gonna just keep it open. It makes our lives a little easier. All right, so the two fundamental parts of a fracture aquifer are the fracture and the matrix. So now let's talk about some ways that we characterize a fracture network. So by a fracture network, I mean a series of fractures and network blocks. It's a collection of fractures and matrix blocks. All right, and some ways that we characterize these that will become important to us are, let's talk about this. There's the width of the fracture. So B is the fracture aperture. That's the width of the fracture. And two other measurements that I'll highlight here. So the first, I'll call this S. And that's the fracture spacing. So for us, the most important characteristics will be this sort of one, the fracture aperture, and two, the fracture spacing. And then I'm going to just define one other measurement that's going to help us derive a few properties of the fracture network. And that's this length that includes the fracture spacing plus two fracture apertures. We'll call this L, where L is equal to S plus 2 times B. And I'm going to define one other thing for us here as we go on. And we're just going to say that these blocks have some arbitrary height, h. All right. This is whatever it is. Okay, so we have fracture aperture and fracture spacing. And then I'm gonna combine these two into a term that we call fracture density. Or all right, so fracture density is the number of fractures per unit length. So we're going to call that N. And it is defined as the number of fractures per unit length. So this would be, for example, fractures per meter, number of fractures per meter. So if, for example, L happened to be 1 meter here, we would have 2 fractures per meter. In fact, doesn't matter what L is, it would be here, if these are evenly spaced parallel, it would be 2 over L. Would be my fracture density. Because I'll always, because L goes from, includes 2 fractures here, right? It'll always be 2 over L. You have to know what L is here, but if we did, we could calculate the fracture density as 2 over L.
Is that just in general, or is that just for this case?
Let me put it this way. Fractures in the real world, we're going to consider parallel sets of fractures. All right, those are super hypothetical and imaginary beasts. There is no perfectly set of parallel fractures in the world. So when we try and characterize these things in real life, it becomes much more messy. But for us, theoretically, we're going to consider parallel fractures. And in that case, it is always 2 over L. Now, turns out, you know, if you've taken structure, depending on the stress state, we tend to end up with sort of a certain orientation of fractures. So subparallel fractures are not uncommon, but they're never perfectly parallel. And they often have crisscrossing patterns. So a lot of this is just developing terminology and then thinking about how we would define a few other terms. Okay, one other fracture network parameter that we'll talk about here, and that is fracture frequency. And that will give this symbol phi. And that is defined as B, the fracture aperture, over S, the fracture spacing. So I'll put this note up here for parallel fractures. All right, so basic terminology: matrix blocks, fractures. The width of the fracture is the aperture. The distance between the fractures is the spacing. And fracture density is just the number of fractures over some length. All right. And fracture frequency is the aperture divided by the spacing. Basic characteristics of a fracture network. All right, so I'm going to zoom in on one fracture here for a second. And I want to talk about what so let's zoom in on a single fracture. All right, and so I've got my matrix block here. I've got my fracture. I got my other matrix block. And this has some aperture B. All right, we're not going to derive it here, but if you take a fluid dynamics class, one of the sort of first problems you'll solve is if you have laminar fluid that's not moving turbulently, all right, through parallel plates. So laminar flow, laminar incompressible. Flow through parallel plates. That's horrible spelling. Plates. There is a solution that gives us discharge through these parallel plates. Is negative rho water, G, B squared over 12 mu times delta P. Don't worry about the negative. It's just like, is it flowing in or out? It's just the vector. Okay, so this is flow through a single fracture or through parallel plates. We can compare this to Darcy's law. All right, so that would say Q negative rho water G B squared over 12 mu times the area times dH dL. And what this says is that the hydraulic conductivity of a single fracture, Kf, is equal to rho water G B squared over 12 mu. So the aperture of your fracture determines your hydraulic conductivity. And it goes as the squared. All right, and what this means is small increases in fracture width mean big increases in hydraulic conductivity. Oh, this is the change in pressure. So this is sort of relationship number one. Hydraulic conductivity of fracture goes as the aperture squared. All right, so now I'm going to break up the area of this fracture. So remember that this, we define this as H here. So if I want discharge coming through this fracture, what's the area of the fracture here? Across which flows coming out of the board here, let's say. So what's this area? So the flows, I want the area normal to the flow. So that would be the area of the fracture right here. What is that? How do I calculate that? B times H. So I can put that in here for A. So I can rewrite this Q fracture is equal to negative rho water G B squared over 12 mu times B times H times dH over dL. And this guy now, remember, this is really K sub F, right? Times B times H. So if I take the hydraulic conductivity of an aquifer and I multiply it by the thickness, what property is that? Yeah. So recall, K times B. So look, I've got KF times B right here. So I can rewrite this as Q is equal to negative rho water G B cubed over 12 mu times H times D H DL. And this now implies that the transmissivity of a fracture is equal to negative rho water G B cubed over 12 mu. And this is another important relationship, and it even has a name. It's called the cubic law. All right, and it says the transmissivity of a fracture goes as the cube of the aperture. What this is basically saying is, as I increase my aperture, I not only increase the hydraulic conductivity, but I also increase the area across which flow is occurring, right? So what it means in practice is that small increases in aperture mean really big increases in discharge. Okay. Let's now go to thinking about a parallel set of fractures. And here I'll draw it out again. I've got these matrix blocks of sort of uniform size, separated by, ooh, that's a horrible matrix block. All right, so these are uniform matrix blocks separated by fractures of the same size. And again, we've got this distance from wall to wall is L. This distance is S. This distance is H. So let's just consider a set of fractures and we can arbitrarily set L and H to well, let's just do this. So I want to calculate the area over which flow occurs for this set of fractures. And I can do this through some dimensional analysis. So first, the height, H, would define the height of our fracture, right? Then we've got the aperture per fracture. Right, that's this, B. But it's per fracture here. The only reason why I've put the per fracture here, I've said that these fractures are parallel and that they're constant aperture. But I'll show you why I put this fracture per fracture here, because then if I say number of fractures, per unit length, so I've got fractures and fractures here, so they'll cancel out. And then L is length. So this is the area over which this is the area of fractures over which flow is occurring. Okay.
Sorry, is the length and the big L the same?
They're not the same. L is a measurement here. L is this distance. This is per unit length, per unit length. Okay, what is so this is B per frac. All right. What is the number of fractures per unit length? We defined that already. N, which is? Okay, 2 over L, but it's also, what did we? Fracture density. So that's N, the fracture density, all right, times L is equal to the area of fractures. Now, what's important here is that H and L are arbitrary. I've just sort of said, okay, consider these general dimensions H and L. So here, if I just say, well, I'm gonna make them, because I've arbitrarily defined them, I'm just gonna make them equal to 1. All right. make this one equal to 1, like whatever unit I'm in, 1 meter, for example. Then this is the aperture, and this would be the number of fractures per meter times a meter. And I would end up with the area of my fracture network is equal to B times N. And this is, because I've defined these equal to 1, this would be per unit height and per unit length. All right, so the area of flow across which water moves through my fracture network is the fracture aperture times the fracture density. Okay, because these fractures are the same aperture, the conductivity for my fracture set is equal to the conductivity for a single fracture times the total area of fractures. So the conductivity of my fracture network is equal to the conductivity of a single fracture. So KFS, this is my single fracture. All right, times AF. And this, if I insert this equation above, is equal to B times N. Okay, so the hydraulic conductivity of my fracture network is equal to the hydraulic conductivity of a single fracture network or a single fracture times the fracture aperture times the fracture density. All right, so I'm going to go one step farther now. I'm going to say, all right, let's write Darcy's law for my fracture network. So it's KFN times AF well, we'll just say this. We can rewrite this now. Is equal to the hydraulic conductivity of my fracture of a single fracture, right? That was rho water G B squared over 12 mu times B times N. And this says that the hydraulic conductivity of a fracture network is rho water G B cubed over 12 mu times N. So this implies that if I've got a set of fractures, which I hardly ever have a single fracture, I've always got a set of fractures. My hydraulic conductivity is a function of aperture. And it goes as B cubed. All right. And my fracture spacing. And here characterized as the fracture density. And so hydraulic conductivity of fracture network is characterized by these two things, but aperture, because it's raised to the cubic power, is far more important. So the most important thing characterizing hydraulic conductivity of fracture network is the aperture. Okay. So main take homes I want you for fracture networks. Fracture and matrix are the terms we use to characterize the fractures and the matrix. All right. The fracture aperture and spacing control how much hydraulic conductivity you have. And it is extremely dependent upon the fracture aperture. And the fracture aperture does not need to be very big. So let's take 5 minutes here before the break. And we'll go back up to the single fracture equation here. Remember KF. All right, let's think about the hydraulic conductivity. So calculate KF. In meters per second for a fracture aperture of, we'll go 5 micrometers. Anybody know what a micrometer is? 5 times 10 to the negative 6 meters. And just to sort of give you a scale, this is 5 times 10 to the minus third millimeters. This is tiny. I think a human hair is like 100 micrometers if you have thin hair, right? Okay. Some constants you may want to know: viscosity 1 times 10 to the minus third. This is Pascal seconds. And you're going to want to use Rho sub water is 1,000 kilograms per meter cubed. And G is 9.8 meters per second squared. If you use all these, you'll be in the right units. Okay, so equivalent porous media. All right. The idea of equivalent porous media is that if we zoom out, what we'll see so if we zoom out, or in other words, scale up above the fracture network scale, much larger than the fracture spacing. All right, so if our fracture spacing is like on the order of a meter, but we start considering, groundwater flow over kilometers, all right, we're at a much bigger scale than the fracture spacing. And when we do that, we'd end up with these like little blocks of matrix, right, and separated by fractures. And it starts to look like porous media. But now my pore network is my fracture network. And my sediment grains are characterized by whatever material rock, full rock I have. And in that case, we can write equations for the equivalent porous media. All right, and the properties of it. And so this is a really common way to treat porous media, is to say, hey, we're not gonna worry too much about flow in discrete fractures. We're gonna try and zoom out and treat this thing like a porous media. The important thing here is we then have to realize that we are only looking at average, like discharge or head over many fractures. All right, so it's not going to be able to give us a prediction about how much discharge we're going to get out of a single fracture. It's going to give us a prediction about what is the average discharge we're going to get over many fractures. All right, if that is the case, then we can write the equivalent hydraulic conductivity KEQ, all right, is equal to the hydraulic conductivity of the matrix plus area of fracture over the area of matrix times the hydraulic conductivity of the fracture. Over 1 plus the area of fracture over the area of matrix. Let's pull apart AF and AM really quick and see whether we can simplify. So this is our first equation, and let's see if we can simplify this. So we got these matrix blocks, right? And if they're parallel, and so for parallel and uniform fractures, we can consider let's look at a line that goes from the half aperture to the half aperture. And we've got some height here, H. And let's call this length here, we'll call it little L. All right, and it goes from halfway through to halfway through. All right. So let's think about what is the area, and this is a unit cell. So if we characterize this, we're characterizing the ratio of the area of fracture to the area of matrix for all of our fractures because they're uniform and parallel. And remember, this is S. All right, so the area of the matrix, A sub M, would be L, or sorry, S times H, right? The spacing times the height here, H. And A sub F here would be 1/2 of an aperture plus 1/2 of an aperture, which is what? 1 aperture. B times H. So for parallel and uniform fractures, I can insert these two in here for A sub F and A sub M, and I will get KEQ is equal to KM times A sub F, B times H over S times H times KF. Yes, yes, very good, thank you. Plus 1 plus B times H over S times H. And these H's all cancel. So we get KEQ is equal to KM plus B over S times KF, 1 plus B over S. And this is the equivalent hydraulic conductivity as if we were considering this fracture network to be a porous media. So we need to know the aperture and we need to know the spacing. We need to calculate the hydraulic conductivity of a fracture, which we know how to do. So we need these three things to calculate the equivalent port, and we need to know the equivalent hydraulic conductivity of the matrix. Yeah, Finch. Well, it's basically because these are lines of symmetry. So if I cut a line right here, and these are parallel, then these, like, the reason why you do this little L here that includes half aperture is because these are lines of symmetry. So if I characterize A sub F and A sub M for this particular area right here, because it's symmetric on either side, I am doing it for the entire fracture network, for parallel and uniform fractures. That's why you do it that way. There is no line of symmetry if I did it from here to here. That's not a line of symmetry. This is the line of symmetry. If I put a mirror here, it reflects exactly across that line right there. But if I put a mirror here, it doesn't reflect, right? It doesn't reflect. So that's why we do the half aperture. Good question. So this one is only really valid for parallel and uniform fractures. But what we often do is say, well, we're going to characterize the fracture network and we're going to calculate average spacing and average aperture, and then we'll use this equation. All right. So similarly, so this is equivalent hydraulic conductivity. The other one is equivalent porosity. Yeah, it's just whatever. So like, for example, in the belt rock, you know, you would have to like drill and take a chunk of matrix into the lab, the core of it, and you could measure the hydraulic conductivity. And for example, it might be something like K equals 10 to the minus 8 meters per second or something like that. But it's just the normal porous media hydraulic conductivity. All right, equivalent porosity basically is the exact same equation. All right, so except that N equivalent is equal to the porosity of the matrix plus area of fracture times area of matrix times the porosity of the matrix over 1 plus area of fracture over area of matrix. Now, this is where the open fracture might come into play. So, for open fractures, parallel and uniform. So if my fracture is completely open, all right, no sand in it, nothing like that, what is the porosity of my fracture? 1. The pore volume to total volume is 1. So in that case, open fractures imply NF equal to 1. And if they're parallel and uniform, we can do this exact same area, calculate the area of matrix and the area of fracture in the exact same fashion, and we get NEQ is equal to NM plus B over S over 1 plus B over S. Okay, so your second homework question is, as part of our research, we've gone out and tried to characterize some of the fracture networks in the belt rock, all right? So I've given you average fracture spacing that we measure in belt. I've given you, we estimated fracture aperture, all right? So I've given you fracture aperture, and I've given you some estimate of the likely porous media matrix, hydraulic conductivity, and porosity. And what you have to do is calculate the effective hydraulic conductivities using these equations, all right? Then we're going to see how those compare at all to what we measured with the slug. All right? Okay. So we've covered fracture porosity, fracture hydraulic conductivity. The next thing that we're going to get into is aquifer characterization and the interpretation of pump tests and slug tests. I'm not feeling particularly amazing, and I'm just trying to decide whether in 20 minutes I'm just going to get us halfway into this conversation. So I'm thinking of calling it early today. But what I'm wondering is we could, I'm just going to call it. So I will post the homework assignment. I'll go back and get it up on Moodle now. All right. You can already do the first. You've already done the first. You can do the second. On Tuesday, we will start with aquifer characterization and interpretation. And you will learn how to do a pump test straight away and interpret the pump test data. All of the analyses that you're going to do as part of this homework assignment are going to be what you put into your final project report. So we'll essentially perform all the analyses we need to perform, so that my hope is after you turn homework 4 in, it's basically writing up and reporting what you've done. All right, so Autumn, I guess we've got some time now. What questions did you want answered for your cross sections?
Yeah. So excess does mean cross section.
Yes.
Okay. And then I got the water table one answered.
What did you do for the water table?
I asked the group chat, and they said it was like the level of the stream, also the level of the alluvial wells.
Yep.
And then okay, so the depth of the wells at the field trip, you said one of the wells was it had a 10-foot screen from 46 to 56 feet. But in the packet, it says for M.1, the total depth from ground of the well is 51 feet.
So for sure, just reference the borehole log.
Okay.
So whatever I said in the field, I was just trying to pull off the borehole log, and I could have very easily misread it right there. So just, you know, Cam's the one that installed the wells and put them in, and she's the one that logged it. So.
Oh, and then my other one was for well locations. Do you just want us to say M.1, or do you want us to be like more specific than that?
No, M.1 is fine.
Okay.
And the locations in the cross sections don't have to be like perfect. They need to be some, you know, hey, it's a conceptual cross section. You want them to be sort of relatively in the right place. So what I usually do is draw a cross section line, put my wells on it, and then so I look in map view, I draw my cross section line, I put my wells on it, and then I draw the cross section from that cross section line I drew in map view.
I kind of have a question about that too, because say like all the wells are parallel to the stream, but if I draw the 3, I know the stream eventually like turns around, so you can make it towards like 3 wells and then the stream.
Yeah, so this is a great thing, and this is actually makes what the Bureau's trying to do. This is a question worth talking about, at least until my computer dies. Add. All right, so yeah, we were up there and we had the river is flowing and it's meandering and doing its thing. So this is downstream here. And we had 3 wells, and they're kind of like, here's M.1, here's M.2, and here's M.3. They're kind of like this. And then the staff gauge is kind of down here somewhere. Is that right? No, they're on the other side of the river. Here, let me. So we got there and the river's flowing. I'm just going to do it this way, river flowing up. However it does. And we got there and the wells are like here. This probably answer your question a little better. Or just discuss it. I don't have an answer to it. All right, the wells are kind of parallel to the water flow. And then the staff gauge was kind of downstream from where the wells were. I've thought a lot about this problem. You've got one measurement of the groundwater head, and depending upon where you compare your staff gauge measurement, the river up here might be higher than the wells, and the river down here might be lower than the wells. It's probably the case than the water in the well level. There's no perfectly right or wrong way to draw this cross section. All right, so because you've got data here and here, I would try and draw a cross section that did something like, personally, I'd do something that did something kind of like this and split the difference. So this would be A to A prime. And then what you do is you project each one of these wells onto here. Now, they're all in the same location there. And that's fine because MDOT, these two are in the same depth, same aquifer, same configuration. So, and in fact, I don't even think Cam gave you a well log for MDOT for one of them. I think MDOT 2. She just gave us the well log for MDOT 3 because they're in the same aquifer. And for all practical purposes, horizontally, these are pretty much in the same location. Even though when we were there, they were separated by whatever, 10, 20 feet, they're very close relative to their distance to the river. So in fact, we call those wells where we've placed them pretty close to each other, we call them a vertical well nest, just because there's not much horizontal distance between them, all right? So in this one, I would actually probably, on my cross section, project them both onto the same place on my cross section, but M.1 would be deep and it would give me the full log down to depth, and M.2 would give me the shallow log.